Okay, let's get started. Welcome to today's talk. First, I want to ask the audience, how many stars do you think there are in our galaxy? Any guess? 1 trillion. Slightly less, but we really don't know. So about 100 billion, maybe, to 1 trillion. I mean, if you count very faint stars.
So I'm right.
Yes. And then how many planets there are?
Order of magnitude more.
I guess I cannot prove you wrong. But yes, I think there are as many stars. Sorry, the number of stars and planets are probably comparable or even more. So understanding the formation of all these planets is a very important topic. And today we are very happy to have a world expert in the formation of extrasolar planets to tell us about this exciting field. Professor Armitage got his PhD from the University of Cambridge in 1996. After postdoc positions at MPA and CETA, he became a faculty at the University of Colorado since 2002. He's a world expert in accretion phenomenon, which can be found throughout astrophysics, such as the formation of stars and planets, and AGN or supermassive black holes. He's also an expert in extrasolar planets. So let's welcome the speaker.
Thank you. So can everyone hear me?
Yes.
Good? Good. So what I'd like to talk about today is some aspects of the formation of planetary systems, focusing on the new things that we think we've learned following the discovery of extrasolar planetary systems. So as we were just saying, and I think everyone knows, the enormous revolution over the last 20 years has been the discovery now of several thousand confirmed or very likely candidate planetary systems, both from observations on the ground and more recently from space. So that's meant that we've gone from a situation where we knew something about one planetary system, our own solar system, to having a very large statistical sample of planetary systems that we can say something about, albeit with, of course, much less information than we have in the solar system. So the question we're going to be posing really is, well, what has that new information taught us about how planets formed? Are the theories that were developed to understand the solar system still appropriate for understanding this much larger sample of planetary systems? So here's the outline. I'm going to begin by discussing some physical principles of planet formation, and really just to emphasize that although in detail the formation of planetary systems is a very complicated process, and it involves some quite difficult and messy physics to do with dust and solids and materials and so forth, we can at least understand some general properties of the solar system, at least, from quite basic gravitational dynamical principles. I'll then discuss something about giant extrasolar planets, so planets we're thinking about Saturn, Jupiter, planets of that kind, which were first discovered now something like 20 years ago, and try to give an indication of how it is that those planetary systems, which at first sight look very different from the solar system, may have actually formed from the same sorts of physical processes, but have suffered evolution after their time of formation to give them what looks like a different character today. And then I'll finish up discussing terrestrial exoplanets. So that's the excitement of the last few years, the discovery of the first planets that are plausibly rocky planets, maybe with radii somewhat similar to the Earth, maybe in some cases in that so-called habitable zone away from their star, where liquid water could be stable on their surface. And it turns out the discovery of these objects has also posed some theoretical puzzles, which are not really very well understood. But I'll be saying a little bit about some ideas we have about what is going on in that case too. So we can first of all ask, well, what can we observe of the planet formation process? And as I mentioned not so long ago, about the only things we could observe were the properties of the solar system, the planets in the solar system, and then we could also make laboratory measurements of meteorites, primitive pieces of the solar system, which had happened to land on Earth. Now we have a much better situation in that we can really say something at least about the initial conditions for planet formation and about the typical outcome of the planet formation process. So if we think about early times, we can observe so-called protoplanetary disks. This is a radio image made in the millimeter with the sub-millimeter array. So this is a disk of gas and dust orbiting a young star relatively close to the sun, containing the raw materials, the gas and solid material that will eventually form, we think, planets. Then moving on, we observe other classes of objects that are known as transition disks, which maybe are intermediate between the early phase where the disk around the sun, around the star, is gas and dust rich, to where it's becoming poorer, perhaps, in gas and dust, perhaps reflecting the fact that the planet formation process is coming to completion in those systems. So this is an ALMA image from last year. This is so-called IRS-48. It's another relatively nearby star. This is observed with ALMA. Then at somewhat later times, we observe other sources which we call debris disks. This is a famous one. This is Beta Pictoris, where what we believe is going on is that the gas in the protoplanetary disk is gone, but we're left with perhaps a large population of perhaps asteroid-sized objects which are continually colliding into each other and producing small dust particles, which are then persisting for maybe tens of millions, or in some cases hundreds of millions of years. And then finally we observe planets. We have the solar system, of course, and then we have a large sample of extrasolar planets, now measuring in the thousands, most of which are observed still around quite old stars. So stars which are billions of years old, perhaps of comparable ages to the sun. So this suite of observations tells us quite a lot about the planet formation process. At these early times, we have gas and we have dust, and we can maybe directly observe the dust up to sizes of about 1 millimeter, so small macroscopic particles that are formed within the disk. These transition disks, this is an image of the dust emission in one of these transition disks. They show some interesting structures. They can sometimes be very non-axisymmetric distributions of dust around the star. So that's maybe telling us something about the interaction between small solid particles and the gas in these disks. These debris disks are saying something about collisions, because that's where the dust is coming from. And then the planetary systems are today governed by purely n-body gravitational dynamics between the basically point masses which represent the planets. So we know quite a lot, but there are also things that are missing. And the most striking thing that is missing is that we don't really have any observational handle on anything between millimeter size scales up to quite large objects of tens or hundreds or maybe even thousands of kilometers. So even though we presume that maybe in these young disks there are many asteroid-sized bodies already formed there are no observations we can make now or in the near future that give us direct information about those size scales. So those larger objects of kilometers and larger, I'll be describing in this talk as planetesimals. We also don't have any examples or any very clear examples of planets that have already formed within their gas disks and are interacting with their gas disks. Some people believe these transition disks have planets orbiting within the disk, but we don't have direct evidence for that. And then finally, we don't have very many examples, or hardly any examples, of really young planetary systems. So even though we have these thousands of planetary systems now discovered, they're at ages of billions of years. What a typical planetary system would look like at 100 million years, perhaps, after the formation of the planetary system is still unknown. So we have to turn to theory, and let me first just sketch the sort of big picture of how we think things might proceed. And so what you're looking at here is time in years on a logarithmic scale on the bottom, and then sizes of solid objects on this vertical axis, going from rather small scales, micron-sized scales, up to the scales of planets up at the top here. And what we think is that the raw material for forming planets is initially dust, so it's micron and submicron sized particles of silicates, ices, and so forth, which are embedded within the gas of the protoplanetary disk. And we have pretty good evidence, both from theory, lab experiments, and observations, that that material can rather rapidly accumulate into objects that are maybe a millimeter or a few millimeters in size. So even at a young time, 100,000 years, a few 100,000 years, this dust, some of it has grown up to millimeter sizes, but it hasn't all grown to millimeter sizes. Some of it is staying in very small dust particles, which we observe. And so what we think is happening is that on these small size scales, there's some kind of equilibrium between objects colliding and coagulating and colliding and fragmenting back into smaller particles. And that probably persists for the entire length of time that the gas is present, which observationally takes maybe 3 or 5 million years around a young star. Now there's also evidence, here from evidence in the solar system, that these small particles, millimeter-sized particles, can grow quite rapidly into kilometer or larger objects. And these objects, so-called planetesimals, are significant because once you get to kilometer or larger scales, then the gravity between those objects starts to become larger than the aerodynamic forces they feel from interacting with the gas disk. And as I say, in the solar system, from looking at meteorites, we think that this planetesimal formation happens relatively quickly, perhaps a few 100,000 years, but is also extended. And so those objects are perhaps continually forming over several million years in the solar nebula. But we don't know how that happens. So we really don't have a clear theoretical picture of how you go from millimeter sizes, several orders of magnitude up, to kilometer sizes. But then once we form these planetesimals, we have a better idea of what happens thereafter. We think that in some parts of the protoplanetary disk, those planetesimals collide rather quickly, and they produce maybe objects of 5 or 10 Earth masses, which are then the cause for forming the giant planets. And the giant planets contain a large amount of gas, so they must have accreted that gas during the few million year lifetime of the solar nebula. So that may happen predominantly in the outer part of the disk, where there's a lot of ice present, and collisions can occur rather faster. Then in the inner part of the planetary system, sort of in the Earth region, we think it takes rather longer, and as I'll show in a moment, we think it maybe takes somewhere between 50 and 100 million years to complete the assembly of the Earth and the other terrestrial planets in the inner solar system. Now, at the end of that process, we still have perhaps a lot of planetesimals left over. Those can collide and drive down the material back into small objects, producing dust, which is what we see in debris disks around relatively young stars. And then finally, of course, once we form these planets, there are then somewhere between 10 million years and several billion years of potential gravitational evolution in order to observe, see what, or produce what we observe in the solar system and in extrasolar planetary systems. So let's focus now on this piece of the story. Let's imagine somehow we formed a distribution of planetesimals. How are we going to form first terrestrial planets and then also the cause of giant planets? So some of this, some important aspects of this, can be understood purely on dynamical grounds by thinking about how a gravitating protoplanet would interact with other material, other solid material, which is orbiting close to it in the protoplanetary disk. So here we have maybe the star, here we have a growing protoplanet, and then we imagine that there's a large swarm of small material, which we might think of as something like asteroid or comet-sized objects, which is moving in basically Keplerian orbits with some small component of random velocities with respect to this object. So we can define two properties of these gravitational encounters that will occur between these small objects and the large one. So the first of those is something we describe as the feeding zone. And this actually follows from very basic gravitational dynamics that was worked out, for example, by Hill, studying the motion of the moon back in the 19th century. And the idea is simply that if we have one massive object, which in this case would be our growing planet, and then one very low mass object that is orbiting in some vicinity of that object, there will be some range of radii where the gravitational influence of the planet will be enough to perturb the small object onto potentially a collision trajectory. And you can show quite easily that that feeding zone scales as the planet mass to the 1/3 power multiplied by A, which is here the distance of the planet from the star. So that's important for planet formation because that defines, if you like, an annulus or a band around the star where the solid material can potentially be accreted by the planet on a relatively short timescale. Now, if you ask, well, what's the area of that band? That's just, of course, 4 pi A, delta A, 4 pi A delta A, and if you then ask, well, how much mass is in that material? Well, if sigma is the surface density of these small bodies that are orbiting with the planet, that mass will just be given by this expression. And for typical profiles of the surface density with distance from the star, we think the surface density probably drops off something like as 1 over the distance from the star. The mass that is in this feeding zone around a growing planet increases as we move further away from the star. So all else being equal then, we would expect that a growing planet will be able to accumulate a larger mass of material if it's far away from the star than if it's close, simply because its gravitational interactions will be able to draw in more material at those larger distances. And as I say, for a sort of typical assumption about how the solid material is distributed, that mass might scale something like proportional to the distance from the star. Then the second property that's important is, well, what happens if the planet perturbs one of these small bodies onto a close encounter trajectory? Okay? So we imagine now that we have an object that's within the feeding zone. After some period of time, it suffers a close encounter with this growing planet, and the three basic things that can happen are that the two objects can collide, accrete to grow into a larger object. There can be a scattering interaction where the small object is perturbed onto a different orbit but remains bound to the system, or finally the small object can actually be ejected from the planetary system entirely or put onto a trajectory where it collides with the sun. And which of those happens depends on the ratio between the escape speed from the growing object and the encounter velocity, which is proportional to the orbital speed. And so if you think about how that works, that depends on the square root of the distance from the star divided by the square root of the planetary radius there. So if we go far out in the planetary system, a planet of a fixed mass is more able to eject material from the planetary system than if it's much closer to the star. So in our solar system, Jupiter is the planet by far which is most able to eject material from the solar system. We think Jupiter has ejected a tremendous number of comets, which ended up populating the Oort cloud of comets. So if this ratio is large, we get scattering or ejection. If it's small, we get collision, and the balance between those things will depend on the distance we are from the star. So we can ask how that would work if we think about terrestrial planet formation, and then also about giant planet formation. So what I'm going to show here is a movie. It's a simulation by my collaborator Sean Raymond, where here we're looking at distance from the star in astronomical units, so the Earth would be here. And what we're going to be looking at is the eccentricity of planetary embryos which are assembling to form the terrestrial planets. And here we've color-coded these objects, these initial planetary embryos, by the amount of water that you would expect the minerals that made up them to have at the time when they formed. So in the inner part of the terrestrial planet region where the Earth is, we expect the material that formed there was initially very dry, it had a very low water fraction. Out where the asteroid belt is now, we observe water-rich asteroids, and we think that the primordial planetesimals would also have been water-rich. So if we play this movie, you can see what happens. The objects scatter gravitationally off each other, so they develop some eccentricity, and then they start growing, starting from the inside, where the timescales are shortest, and progressing further out in the planetary system. And what you can also see maybe is that as time progresses, there's some mixing between these different regions. So the water-rich material that was out in the asteroid belt starts becoming mixed in with this very dry material that was initially in the terrestrial planet region. And here's the time here in millions of years. What you find in this kind of calculation is that on a timescale of something like 100 million years, you end up with a small number of bodies in the inner planetary system, masses and eccentricities that are not so different from those seen in the solar system, and then you have some unconsolidated material out in the asteroid belt where the influence of Jupiter has prevented any planets forming. So this is an n-body simulation of terrestrial planet formation, but the basic sort of answer you get here can be understood from what we already said. In this region, the escape velocity is small compared to the Keplerian velocity. So terrestrial planets basically grow in place. As they're growing, they do not have enough gravitational influence to eject material from the terrestrial planet zone. So that material ultimately must end up colliding and forming terrestrial planets. And so what you end up with here is basically just a function of how much material you had in that region to start with. If you had more material, you would form more massive planets. and to end up with a stable planetary system, you'd have to end up with fewer of them. You scale down the surface density of solid material, you end up with more planets, but they're much less massive. Here's another visualization of that same sort of calculation. Here again we have semi-major axes and eccentricity. Here we're going to see a space-time diagram of the growth of terrestrial planets. This is a very similar type of calculation. Here are the objects here they're growing. And here you can actually see how much wandering, if you like, there is during the growth process. So objects are mostly growing in place, but they are, as you can see, oscillating to and fro, particularly out in sort of the region where Mars is, where the orbital velocity is lower, and so scattering events between protoplanets become stronger. So you can look at this quantitatively, and the basic answer is that this sort of picture of how terrestrial planets grow actually works pretty well for understanding the basic properties of the solar system. The masses, the almost circular orbits, almost planar orbits that we see in the solar system. There is one problem, which is actually illustrated here in this diagram. Here at the end, you form maybe 3 planets in this inner region. So maybe this is Venus, this is Earth. Out where Mars is, you formed a planet, but it has a mass that is actually comparable to that of the Earth or Venus, rather than the mass of Mars, which is much smaller than the Earth and Venus. And that again follows from what I've been saying. If material is just necessarily colliding in this region, if we had a lot of material in the planetary system initially, in the region of Mars, it would have formed a very large planet rather than the small planet we see. So in the solar system, a lot of interest is devoted to understanding why Mars, in fact, has the low mass that it does.
Venus and Mercury just switch over.
Yeah, so here they switched over. So that sort of thing is fairly common. Now, what about the giant planets? Well, for the giant planets, their defining feature, of course, is that they have a lot of gas, and so they have to become large enough to capture that gas during the time that the gas is present around the young star, which is only a few million years. So roughly that means you need about 5 Earth masses or more in solid material to accumulate, so that would then be able to draw in the gas from the protoplanetary disk and form your giant planets. So this defines actually a sort of sweet spot in distance from the star where that ought to be possible. So if you're too close to the star, for the arguments we already gave, there would be too little mass in the feeding zone to actually produce a 5 Earth mass object for a reasonable initial surface density of solids. If you go too far from the star, then scattering and ejection of material becomes more probable than collisions, and so that material will actually not grow into a large object, it will form many small objects, and if it tries to grow into a large object, it will just start throwing material out of the planetary system entirely. So there's a sweet spot which maybe lies between 1 or a few AU out to 10 or 20 AU, where things are just about right, where there's enough mass in the feeding zone and where encounters lead to collisions, and you can grow large objects quite quickly. So that indeed, of course, is where we see Jupiter and Saturn in the solar system, which is good. And indeed, when people do calculations of this, so this is growth in mass as a function of time, these curves are for different initial assumed surface densities of solid material, it turns out you can form Jupiter and Saturn within a few million years with quite reasonable assumptions in the solar system. So this also works quite well, even though there are large uncertainties in those giant planet formation calculations, mostly associated with the fact that as a planet contracts, it has to lose energy, and that depends on the opacity, how much dust there is that is trying to trap the heat within the planet. Okay, so that's the solar system, and for the solar system, maybe things work reasonably well. When we look at giant extrasolar planets, however, we immediately encounter surprises, and these surprises, most of them, have been known since the first discoveries of giant exoplanets, now almost 20 years ago. So here's the first surprise. Here's semi-major axis, distance from the star, and eccentricity, and these red points here are a small initial sample of giant extrasolar planets. And the blue points are the planets in the solar system. And so there are 2 striking things you see here. One is that there are giant planets of very small orbital radii, so-called hot Jupiters. So 0.1, 0.01 AU. 0.01 AU is just a couple of solar radii, so really very small scales indeed. And then also you see that these planets have a very large distribution of eccentricity that extends up to very high values, values that in the solar system will just be characteristic of comets. So that's an old puzzle. A slightly more recent one is that it's possible to measure the inclination of some of these planetary orbits with respect to the plane defined by the stellar spin. And that's possible for these close-in planets, the so-called hot Jupiters. And when you do that, you find that this angle, which is shown in this plot here it's shown as a function of the stellar effective temperature. We don't need to worry about that for the moment. Some of these angles are very large. So 90 degrees would be a planet that's polar orbiting. 180 degrees here would be a planet that is orbiting the star in the opposite direction to the stellar rotation. So we see that some of these planets indeed are orbiting in the sort of expected plane, coincident with the stellar rotation, but others are substantially misaligned, and then some are potentially retrograde. So this is a puzzle. The orbital properties of these giant planets seen in extrasolar planetary systems are very distinct from the solar system. They can be much closer to their star, which for the arguments we've already given is surprising. They can be eccentric, which again is surprising, completely unlike what we see in the solar system. They can potentially be inclined as well. So what is going on here? Well, so most of these observational results are now old results. So I would say we have a working hypothesis for what is causing those surprises. And the general picture we have is that the planet formation process itself may proceed rather similarly to in the solar system, perhaps extending somewhat closer to the star than the giant planets manage to form in our own solar system. So giant planet formation occurs by this same mechanism of growing a large core of material and subsequently accreting the gas. Perhaps it occurs as close as a few AU to the star rather than out at 5 AU, which is where Jupiter is in the solar system. But then subsequently we have evolution, which is due to the exchange of energy and angular momentum with some other component of the system. And we really don't know for certain what that other component is in the majority of cases. It could be other planets in the system. It could be gas in the protoplanetary disk that is still present when the giant planets form, or it could be a stellar companion in the form of a binary star, which was orbiting the star we're interested in at some early time. So there are these various ideas, which are sort of summarized on this little plot here. One idea is interactions between planets and the gas disk. Here we're looking down at a simulation of that process. So here you have a planet embedded within the gas disk. It produces a spiral wake in the gas disk, and gravitational interactions between the planet and the gas can result in the exchange of energy and angular momentum between the two in that circumstance. It can also result from planet-planet scattering. So here we imagine we have a planetary system initially that contains, if you like, too many massive planets, which are in a configuration that will be unstable over a long period of time. So those planets will eventually encounter each other, they will scatter off each other and develop eccentric orbits as a result of that process. And then we have some other possibilities. One, as I said, is associated with having binary star systems present there. Then there are ideas which are related to things we know about in the solar system. If you have a planetary system with some eccentric orbits, those orbits may be chaotic, and so the eccentricities can wander over a period of time, eventually attaining large values. So we have various possibilities here which have been explored, but we don't have a very full understanding of which is most important. So let me give an idea of maybe the one that I think is most important. I think you can probably explain quite a lot of what we see in giant extrasolar planetary systems as a result of this planet-planet scattering hypothesis. So as I say here, the idea here is the planet formation, perhaps associated with some motion through the gas disk, results in unstable planetary systems at the initial moment when the gas in the disk has been dissipated. And then at some point between that time, which is maybe a few million years after the star formed, and the billion years where we're observing the planetary system, the system becomes unstable, and gravitational interactions between the planets produce eccentricity. So here's a simulation of this. This is work done with Nick Mokel, who's a graduate student in Colorado. And what we were doing here was actually to try and incorporate the effects of gas as well as planetary interactions occurring under gravity. So here we have the gas disk. We start here with 3 planets and allow them to interact with the gas and with each other gravitationally. And what's going to happen here, slow down the movie, is that it's going to be actually a collision between the